morning, everyone, also from my side. My name is Armin Urkanovic from the University of Freiburg. I'm one of the organizers of the workshop. Happy to see so many of you. And I will guide you through this morning by introducing our speakers. And I'll start with the first pair of speakers, which are from my home university. On one hand, it's Christian Nietz, who's a PhD student in our group and also working at Siemens Research. And it's Moritz Diehl. Probably you may have heard the name if you use Kasadi or real-time iterations. That's this guy. And to not steal the time from the speakers, I will just hand the word to Christian and Moritz. They'll split it in two parts, and they will talk to us about numerical optimal control for non-smooth systems. And it's the stage is yours. Moritz can start.
Yes, good morning. Hello. Can you hear me well?
Yes.
Okay. Greetings from Freiburg. I really regret that I couldn't join it. I was looking forward to a visit in beautiful Vienna, but I had to stay for some duties here at the University of Freiburg. So my task is to introduce non-smooth optimal control to you, and then Christian will show you the coolest application we work on at the moment. I think the most industrially relevant, for sure. The setting is pretty standard. It's an optimal control problem that we like to solve in continuous time. You have this Balzer objective here, and you have crucially the ODE, the ordinary differential equation dynamics, x dot equals f of x and u. And what is maybe interesting here to note is that all these outer problem functions, L, E, H, and R, the constraints and the objective, they can usually be assumed to be convex. And so based on this convexity of most of the outer structures, which could be, for example, bounds on states or controls and quadratic tracking objectives, on top of this is the difficulty due to the system dynamics. So it's all in this little f function where all our difficulties come from. And the nicest case is if we have a linear ODE. In this case, this f is a linear or affine map. And in that case, we end up with convex optimization problems, even after discretization. It gets a bit more interesting when we have nonlinear but smooth ODEs, where this f is just a differentiable function. And we typically end after direct methods and discretization in the class of nonlinear programming, which is also a pretty established and mature field of nonlinear optimization. And when we get into non-smooth dynamics, then these constraints that are induced by the dynamics, by the ODE, they lead to strongly non-convex problems, non-convex and non-smooth problems. And we actually discovered that nearly all relevant problems of interest can be reformulated in some form or the other into mathematical programs with complementarity constraints, MPCC, which are therefore also part of the talk today. Let me first say a few words about A and B, the nonlinear and smooth case. They, as I said, can be solved reliably and fast nowadays by what we call Newton type optimization. That means using derivatives. And one prime application example is nonlinear model predictive control, which I will only show in two applications to give you the spirit of it. Here's one beautiful application at the University of Zurich, where people re-optimize online very fast the trajectories of drones that should go through goals. And what you have seen so far was in the computer, but now it's also in the reality. And the crucial feature is that you always predict a bit into the future and then optimize for it. Another application that I also liked a lot was done by a visiting professor at our lab here in Freiburg, who took his beautiful Furuta pendulum setup with the Cortex M7 and then implemented our software Arcados, which is nonlinear MPC, on this setup. It is a simple ODE. You see the full equations here, actually. It's 4 states only. You measure all 4 states. It's as simple as that. And then you do a real-time iteration with 12 millisecond sampling time. And crucially, only 500 microseconds feedback delay. And overall, he predicts 10 intervals on 200 milliseconds. I think this is a beautiful example of what you can create with nonlinear MPC. Without any training, by the way, but you need to identify a model. Latest development is actually differentiable MPC, which is the idea to, let's say, train the MPC inside some simulation loop, for example, in reinforcement learning over MPC. This was just a prelude. I want to start with the non-smooth part now, and let's start with a classification. Then we talk about these mathematical programs with complementarity constraints. Afterwards, I say a few words about open source software. And after this, we hand over to Christian Diehl, who brings the main part of this talk, robust rigid body assembly, his application in Siemens. So when you look at non-smooth dynamical systems, I think it's useful to discuss what's the level of difficulty here. And we discovered that it's useful to distinguish between three cases, depending on how differentiable the trajectory is with respect to time. So NSD1 is a non-differentiable right-hand side. For example, if you had a ReLU activation function or an absolute value, like here, 1 plus absolute value of x, this is the easiest of all cases, but it's still leading to, after discretization, to non-smooth optimization problems, slightly non-smooth, right? NSD2 is already significantly more interesting and more difficult. State-dependent switches, for example, a valve that opens in a chemical plant, or a sign that enters directly into the model equations, like x dot minus equals 2 minus signum of x. And even more difficult are state-dependent jumps, where you would have, for example, a bouncing ball that when it touches the ground, it will invert its velocity, so the states really jump. That's what we call NSD3. And I should say that they are obviously the most interesting and most difficult ones, and they are also related to contacts and robots that touch the ground and so on. So the question is, can Newton type optimization, which is based on derivatives, still be useful for these NSD3 systems with contacts, with jumps, with bouncing balls, and so on? And the answer is surprisingly yes. I should say that I was astonished by this myself. I want to just mention a bit of progress from the last years in this field that was in our environment. The first thing is that you can transform actually these NSD3 jumping systems into the easier switching systems of NSD2 type via what we call time freezing. So that's a nice reformulation trick that isn't affecting discretization yet. It's just a reformulation. Afterwards, you can discretize these NSD2 systems with highly accurate finite elements with stitch detection. They remove spurious local minimizers. So that's another really interesting advance of the last years. And then, as I said, we will end with mathematical programs with complementarity constraints, and that will be solved with a homotopy procedure. You can use open source software, Nosnog, CCOP, Blasfeo, Arcados. I will mention a few at the end. But as promised, let's briefly explain what are these MPCCs. So mathematical programs with complementarity constraints are just nonlinear programs with f, g, and h problem functions here, but with some extra constraint here in red, where the variables w1 and w2 need to be orthogonal to each other and positive. So that's describing this L-shaped set here, which is, of course, very non-convex and very non-smooth at the kinky point. And this constraint degeneracy complicates the theory of computations compared to non-linear smooth NLP. And the main workaround that we will use is that you solve a sequence of more regular NLP. And there are many different methods to do this. But from our perspective and experiences, the Scholtes global relaxation method is the easiest to implement and the most efficient regularization method. I mean, variants of it, of course. And the idea is very simple. You just relax this L-shaped set by a set which is described by three inequalities. Two of them are linear, just positivity of W1 and W2, and then this nonlinear upper bound, which describes this very non-convex and nonlinear constraint here. That's a relaxation. It contains the true feasible set, but it's more. But of course, you can now tighten it, and you reduce this parameter sigma by periodically and resolving these problems. You can get actually very close to the true solution. I should say that an additional idea is to perform these Scholtes and the interior point homotypies simultaneously. That's due to Raghunathan and Bigler in 2005. And we recently implemented that in CCOpt, which is a new open MPCC solver. That brings me to the last point of my part of the talk, which are these recent open source software developments. So let me mention only two most related to this talk here. And these are Nosnog, which implements these FESD discretizations, time freezing, and goes from a problem formulation into a high accuracy time discretization and then solves it with different methods. And one of the methods is CCOpt. CCOpt is, let's say now at the moment, a core effort of our team, in particular here Anton Posarski and Armin Nurkanovic, Jonathan Frey and François Paco in France, that collaborate on this solver, which is based on MAD-NLP and is based on, it's possible to extend it with GPU support. It will be available in Kazadi, and if you download a pre-release of Kazadi, you can already use CCOpt. It's a fast solver for optimization with complementarity constraints. Before I hand over, I want to show one little example that was generated with Nosnog. It's just the aim to have this little disk activated by two arms that can touch it, and it should just be at the top position in a different rotational state. And that's the only objective you impose, and you give this to the solver with, of course, this very nonlinear and non-smooth NSD3 dynamics, and you solve it, and at the end you get the solution after 10 seconds, which is then doing what you want with a very complex motion where actually the solver decided when to touch and when not to touch. I find that remarkable, and there's thousands of other examples. But let me just give you my personal conclusion or a personal observation that I want to emphasize, and that is that I think that the great watershed in optimization is not between convexity and non-convexity, as we usually think, but it's between computer functions that do or do not provide derivatives. And I think this is something to keep in mind, because a lot of people in robotics nowadays use simulators, which are computer functions, and are too lazy to ask them for the derivatives or for these tricks with MPCCs and relaxations. And you can do a lot of things by just calling computer functions, but they are computer functions, and you can ask them to give you derivatives, and I think you should do. And that's one thing that is actually at the backbone of deep learning, right? The only reason why backpropagation works is because these are computer functions that are written with view of derivatives. I mean, it's this community, I don't need to stress it, but I just think it's important to keep in mind that just out of laziness, a lot of people just use derivative-free optimization. And with GPUs, you can do a lot. You can parallelize and you can be fast, but you will never be as fast as you can be when you get derivatives. So that's why I think look for how you get the derivatives out of your model equations if you have them. With this, I want to hand over to Christian, and Christian will now share with you the application at Siemens.